So welcome everyone to the BioInfoSummer public lecture. Before we begin proceedings, I would like to acknowledge and pay respect to the traditional owners of the land on which we meet, the Gadigal people of the Eora Nation. It is upon their ancestral lands that the University of Sydney is built. As we share our own knowledge, teaching, learning and research practices within this university, may we also pay respect to the knowledge embedded forever within the Aboriginal custodian of the country. And so not all of you are attending BioInfoSummer. This is a public lecture. And so it's probably actually really important to tell some of you what BioInfoSummer is. So let's look it up. So AMSI BioInfoSummer is this wonderful education initiative. What's the word for start? Initiated by AMSI. And so it's a wonderful initiative designed to teach people with either a computational background or a biological background more about bioinformatics. I think it's been quite successful, and it does this by pulling in international and national highly recognized researchers from the bioinformatics space to share their learning. And so this is a safe place where people can come to learn a little bit and hopefully build the networks that are kind of going to progress with them throughout their eventual careers. And so because of this, at least the mission goal of BioInfoSummer, Rafa is actually a real ideologicalized, idle aspiration, something along those words, of what BioInfoSummer probably wants to be or who they kind of want to promote. So again, if any of you actually bothered to read anything about Rafa or know anything about Rafa, he is prolific in the bioinformatics space. He was one of the founders of Bioconductor. Hopefully half of you are at the BioC Asia conference, and so you might know what Bioconductor is. The other half of you have sat through enough workshops by now to know how important this curation of well-documented software is. So he's been a real driving force in making sure that bioinformatics is open source and also digestible. He's also been, I don't know how you do it, but he's also been quite adamant in keeping up education just in the statistics and data science space. So if any of you want to be educated about data science, he has a free, open, accessible introduction to data science textbook on GitHub. It's great. I use it in my courses. It's brilliant. He also has, in collaboration with others, an edX course on advanced genomics. Do you want to give us a name? What's the name of some of the qualifications people can get on edX?
Well, the data science professional certificate.
The data science professional certificate. So if you'd actually like a little rubber stamp to say that, hey, I'm actually a qualified data science expert, then edX is the place to go. And it's brilliant that Rafa contributes to these things. So there's tens of thousands of people that have done these courses. And so in that sense, Rafa's really combining the education space with the bioinformatics research space. And I think that really brings together the heart of BioInfoSummer, combining hardcore, cool, really awesome research that we see in the mornings and going in and actually being educated on how it works in the afternoons in some of these workshops. There was a lot of apprehension, I think, on Tuesday night in our careers evening. Who here actually went to the careers evening? So many of our questions, there was a lot of anxiety, I think, in some of the questions of what do we do next? Do I get into bioinformatics? Or if you're already in bioinformatics, do you stay in bioinformatics? And I think Rafa is actually a really good example of maybe why you shouldn't be so apprehensive or anxious. So Rafa has got a really solid grounding in statistics, and that's seen him through, I think, a very broad range of applications. So yes, he is a bioinformatician, but his passion for science and those quantitative skills, I think, actually make him quite versatile. And I think Rafa at any point could throw himself into anything and be quite successful in it. And if you maybe go and read a little bit about him, he did his PhD in like analyzing harmonies in music signals. Hopefully at some point he'll mention something about his Hurricane María analysis. that he did. So he's got really, really broad in the things that he does. And so while I've always viewed him just as a really cool bioinformatician, he's more than that, and you can be more than that. So feel confident that no matter what you're doing in the bioinformatics space, whether you're getting into it or leaving it, everything's going to be fine if you work on those skills, have a real passion for understanding problems and really liking science. And so with that speaking, maybe we can give Rafa a clap and he can give us a proper introduction to what he wants to talk about.
That was more than 2 sentences, but okay. All right, well, thanks for inviting me. As you heard, I was in Boston this morning, or was it yesterday? I can't remember anymore. That's what it looked like. And I was very excited to come to Sydney. It's not like my All right. So what I want to do is talk about applied statistics. I work in, as you heard, I work in genomics, bioinformatics. The main expertise or knowledge base that I have that permits me to do that is applied statistics. A lot of the rest I've learned on the job. So I'm going to tell you about cool things that are happening in applied statistics and including some examples from my own research. Oh, okay, sorry, I'll stay right here. All right, so a little bit about my background. So I did a bachelor's in math in the University of Puerto Rico. And then I did a PhD in statistics in UC Berkeley. After that, I joined the faculty in a biostatistics department. I studied, as you heard, I did my thesis in analyzing sound signals. And then around halfway through my fifth year, I realized there was no jobs for people doing that. So I applied broadly, and I think by accident, I applied to a biostat department, and they actually invited me to come give a talk there and try for a job. And the reason why that happened was because they saw that I was good at analyzing time series data, and they needed someone that could do that. So the music part wasn't a big deal at all. It was the fact that I could analyze data with time series knowledge that got me that job. So that relates to some of what you heard earlier about how you doing statistics gives you many ways of working and getting on different career paths. Now, more recently, I'm the chair and a professor in the Dana-Farber Cancer Institute in Boston, and a professor in Harvard. And my day-to-day is collaborating with scientists to have really great ideas, and they produce data and they don't know what to do with it. So that's where we come in and help them out. And it's really a fun job. We get to work on many different things, and many of them we hope, we think that will actually make a difference in cancer prevention, diagnosis, or just improving people's health. So that's my background, and the things I'm going to talk about today will help you see how that all kind of came into what I ended up doing in my day-to-day and in my career. All right, so here's what I'm going to do. I'm going to tell you a little bit about a little background on what I mean by applied stats, then talk about two very popular examples that aren't my work, but are just fun. And it's past 5, so we shouldn't be giving talks that aren't fun at this hour. Then I'll give you one example from my own research in bioinformatics, very short description of what we did, of one of the things we've done. And then at the end, I'm going to give you an example related to estimating death rates after Hurricane Maria, as you heard earlier. Okay, so there's a lot of mathematicians in the room or people studying math, and math was a very important component of many of the great discoveries and inventions of the 20th century. It was basically applied physics, applied math, and engineers made things like cars, airplanes, power grid, television, and digital computers. That's not what I do. I do applied statistics. In the 20th century, applied statistics was also part of important discoveries, not as groundbreaking as these, but there are things like agriculture, answering questions like, does fertilizer increase crop yields? Clinical trial or randomized trials is an important contribution of statistics and making associations with observational data, like the fact that we know today that smoking causes cancer. That was originally a statistical discovery based on observational data. And then also things like predicting the weather, which we've gotten better and better at, because the reason weather prediction has gotten better is because we've moved from using just mathematical models that try to describe the weather phenomenon to models that use data to predict. And the combination is what gives us what we have today, which is very accurate, and at least in Boston. I don't know about here. Okay, so now this is the 20th century. But now, recently, I don't know how many of you are old enough to have seen all these magazine covers that came out about, I don't know what it was, 5-10 years ago. But all of a sudden, there was a big data revolution, and we were hearing about data here and data that, and everything's going to change. And what's this about? How does this relate to what I just talked about? So while the first examples I gave you from how math was so important for important discoveries in the 20th century, those are things that are discoveries that are based on deterministic findings. So you write down the equations, things are predicted almost perfectly, and some engineer applies that in a way that produces something like a car or airplane or a computer. The other examples I gave you from statistics aren't like that. You don't have an explanation of why things are happening. Instead, you collect data, you embrace randomness, and you describe it. You come to a conclusion using statistical analysis. So those are two different things. There's deterministic math and stochastic processes. You want me to use? I can keep myself from. All right. Now I can move. Okay. So now today in the 21st century, I think, and a lot of people think this too, that the availability of data and to analyze in real time will make these coming years, many of the interesting problems are going to be statistical problems based on data. And what I think happened was it wasn't that we had a big data revolution 5 or 10 years ago. I think if you look at the size of data through time, it's been growing at about the same rate in the log scale for decades. But what I do think changed is the fact that around in the 70s, 80s, because computers came along, all of a sudden people were saving data on a computer instead of a file cabinet. By doing that, now all of a sudden you can use that more easily to answer questions. Now I'll give you some examples. The first one I'm going to give you is related to baseball. I don't know if you all know what baseball is. It's like cricket, but not as boring. And there's no tea time or whatever that is. What happens at tea time? Do they actually drink tea? No, I don't know. Anyways, it's very similar. All right, so how do sports teams pick players? So it used to be, and it still is to a certain degree, that it was based on an expert going to games and watching them, like this guy here, watching them and seeing how fast they ran and how hard their jawline was and all this. Is that a fire alarm? No. Okay, so that was, they would base it on experts looking at people and picking the best players that way. And these experts are pretty good. And it turns, and they mostly agreed on who were the best players. So you would have players like this guy here, Jason Giambi, who played for the Oakland A's and was taken away by the Yankees because they gave him a bunch of money. And all these teams were bidding for them, and he goes to the richer teams, get the better players. So teams with no money started using data. This is, I don't know, about 20 years ago now. So what they realized was there was one particular team, it was the Oakland A's, the team that Giambi played for. They had a change of a president or whatever, the owner, in the late 90s that decided that he wasn't going to spend any money on the team. and the budget was only like $20 million, which is not that much compared to other teams. So this one person had this idea of using data to pick players. So what they did was they noticed, and here's what I was talking about, data being on computers. They noticed that the colleges, the universities had their players' data on the internet. So they hired all these kids from Stanford. It wasn't that many, it was maybe like 3 of them, wrote Perl scripts to download all the data, and they started scouring through and finding players that on paper look good, even though maybe the experts didn't think they looked that great, and they built a team mainly based on statistics instead of the experts looking at them. So this was a big success. I even made a movie out of it on Moneyball. I could have watched it on the plane if I wanted to. It was available. One complaint I have about this movie is that the statistician that's him. The statistician that did the work, that's him in real life. This is him in the movie. All right, so the end result here is this is a plot that shows you the average number of wins across 3 years. These are the key years when they were doing this, and this is the payroll. That's in dollars, in millions of dollars. So you can see the Yankees. That's the team that everybody hates because they're rich and they would win just by buying the best players are way out there. So they're the best team, but also the one that spends the most. This is our team. That's why we hate them so much. You can see that there's a relationship, not surprisingly, but the Oakland A's did pretty well, and I think it's because they were using data to pick players. Okay, so my second example that's also very popular, relates to recommendation systems. So here is, if I go to Netflix, this is actually not recent. This is back when they used to give stars. Now they give some other thing. But when I went to Netflix and I searched for the wedding planner, it knew I wasn't going to like it. I don't even have to watch it to know that they're right. So how do they know that? How do they know that I'm not going to like the wedding planner? Oh, they use data to do it. So they use data from other people who rate these movies, and they combine it in a way that helps them make distinction. I'll tell you a little bit about how they do it. And I'll also tell you that Netflix in 2008, they had a competition where they said that anybody that can beat their algorithm by 10% would get $1 million. So the data, by the way, these slides are courtesy of Chris Walensky. We'll find out who it is soon. So here's how it works. So this is the data. Right, so you have the user, the movie, the score, and the date. So they give you this big table with millions of rows. And then they have another table where you don't know the score. And then you have to predict what it is. And then they have a way of scoring how well you did. If you beat them by 10%, you would you got the $1 million. So here's an example of what the table would look like. These are some movies and this is actually real data. You can get this data. No, you can't get the Netflix data. They got sued for making it public. But you can get, there's another group, Movie Lens, that has made it public. So if you look at one thing, so how do you predict, how do you give this star? So the simplest thing we can do is we can just take the average ratings for each movie and just give you that rating, right? So here are the best 10. And not surprisingly, at least when I analyzed it, last time I analyzed the data, these were the best 10. So you can just say, okay, these are the top movies, and I'm going to just say that's the number of stars it gets. Here are the worst. Has anybody watched any one of those? There's usually that has Jennifer Lopez in it too. Yeah, I don't think I've seen any of these. But that's not all, because there might be people that don't like these movies, even though they're highly rated. And there is actually something more you can do to get it even closer, to give you a specific rating for the stars. So here's how they do it roughly. So here is the rate. So if I compute these averages and then I subtract for each person from the average, this is the residual. for each person. So those every dot is a user. And these are two movies. They're both gangster movies, if you haven't seen them. And you can see there's very strong correlation. So people that hated Godfather also hated Goodfellas. And people who liked Godfather also love Goodfellas. This is me. And then there's other movies that correlate. There's Ghost and Pretty Woman, same thing. That's me there. And then there's negative correlation between Ghost and The Godfather. So you can do more than, if you can use this to predict the stars specifically for people by using what other people like them say and what other movies like them say. So in statistics, we have something called factor analysis. That's very old. It's kind of like the 20s, that you can use to try to find from the data what are these underlying things in us that makes us like move some movies more than others in different ways. It's like there's like structure in the data. It's like this group of people likes these movies, these other group. So that kind of data can be modeled with these factor analysis or latent variable models, if you know what that is. So here's this team that won, that was led by a statistician, Chris Wolinski from AT&T. They did this. They fit a latent model, trying to find these underlying sources of variability that explain why some people like these things and others like those. And when you plot the movies in these dimensions, these two dimensions that kind of give you the most variable, so the highest source of variability in the data, you can see patterns already. This comes from the data, not from any kind of expert analysis. If you look at the movies, you can see what these dimensions have a meaning. Like, so here, frat house gross comedies on the left, see them? And then critically acclaimed on the right. And on the other dimension, you see artsy, edgy movies. And on the bottom, you see Hollywood big budget movies. And Wizard of Oz in the middle for some reason. Okay. So that's how they do this. They fit models like this. And they use the structure in the data. They model it, and they can give you a recommendation based on this. That's how you get personalized recommendations. Again, it's completely data driven. All right, my next example is from genomics, and this is work that I did more than 15 years ago now. Wow, almost 20 years ago here in Wehi. I was visiting Terry Speed, and Gene was there too, and we did this work. Okay, so what does it relate to? It relates to gene expression. So this is what gene expression. You might have heard this already in this work in one of the workshops or one of the talks. Is what permits cells that have the same genome to be very different. So here I have all these cells can have the same genome, but then they start having different cell types that are very different. So here's liver and a brain, same genome, very different phenotype and different function, very different. So how does that happen? And one of the ways that happens is that in different cell types, different genes get activated or expressed. So way back when, before the measurement revolution in genomics came, this is what the data looked like when to answer these questions. So here they're asking the question, which cell type is this gene expressed in? So you don't need a statistician to help you, as you can see which one it is. So this is a technique that will turn black when the gene is expressed and won't turn black when it's not. So somewhere around the mid-90s, these new technologies come out that let you do this same thing, but for every gene at the same time. And instead of getting a paper with a black dot on it, you actually get a number. And this is what the data all of a sudden looks like. So now every point is a gene. And here I'm showing you two genes, two different cell types if you want. And you can see that you can look there and see each gene, what the expression is in the two cell types. And so that's what the new data looks like. So now you can imagine, so now you get for each cell type or tissue, you wanna try to see which genes are expressed and which ones are not. So you have a vector of numbers. Right? So now you have 12,000 vectors, a vector of 12,000 numbers for each cell type or tissue. And now that's your measurement. So I'm going to imagine that we didn't know that what made different cell types or tissue types different was the fact that they had different expression patterns. Different genes were expressed differently in the different tissues. So let's suppose we didn't know. So here's some data. This is, again, real data, not simulated, from 5 different tissues. And there's many points because I have different tissues from different individuals. So there's 5 tissues. And the plot is what's called a MDS plot or a PCA plot. And the idea of these plots is that points that are close together, this is 2 dimensions. So the real dimension is 12,000. So we can't make a plot of 12,000 things, 12,000 dimensions. So this is a plot where the distance between these 2 points is approximate to the distance between the 2 original 12,000 number vectors that you start out with. So remember, each one of these points originally is a 12,000 number vector. We reduce it to 2 dimensions where the distances are approximate. So if that being the case, what we should see here are 5 clusters. If it's true that different tissues have different expression profiles or patterns. Here are the 5 tissues, and you can see that it's not quite as clear as we would like it to be. For example, this colon is closer to this placenta than it is to this other colon. So what's happening? Why is this like this? So when we started working on this data, we saw things like this that didn't quite make sense. And one of the things that we started doing was going back and exploring the raw data, rawer data than what I just showed you. This is one of the things that as applied statisticians we do often. We look at data. We learn ways to look at it in ways that we can make discoveries or find out problems. So it's something that you don't necessarily learn when you're taking a math class or a statistics class even, where you just learn procedures and then theory. But a lot of what I do is just look at data in different ways, make plots like this until I find out what's wrong with the data or maybe make a discovery in a more optimistic view. So this is one where we're trying to find what's the problem. Why are we seeing these patterns that aren't showing what we expect to see? So what I'm going to do now is I'm going to take just one of those points, 2 of those points that are supposed to be very similar, like say this one and that one. And I'm going to take now I'm going to go back to the 12,000 numbers. And I'm going to plot the scatter plot you saw earlier. There's the 12,000 numbers there. Every point is a gene. But now I've transposed the plot so that I have the difference on the y-axis and the average on the x-axis. So genes that are differentially expressed in the 2 tissues will be either up here or down here, right? Because they're very different, so the difference is big. And then genes that are highly expressed are up here. Genes that are lowly expressed are down here. So this is actually a plot that a company ran for us. That they ran an experiment where they expect everything. It's a control experiment where they expect nothing to be different, except for those 12 orange points. So these points should really all be at 0. There shouldn't be any difference between the 2 measurements because it's the same material they start out with. But we see all this noise down here. And then the orange ones, which are supposed to be different, they seem to be okay. They're not at 0, which they shouldn't be. But they're hidden away. They would be very hard to find in the noise of the points that aren't supposed to be different. So when we first saw this, we asked our collaborators what's going on, and some of them said, "Oh, that's technology is no good. That's why." Others said, "Oh, that's how biology is. It's just messy." But eventually, we got to Appendix D of the manual of the technology producing this, where all the statistics were described. And we noticed that they were doing some things that maybe could have been done differently. I'll actually show some symbols, some mathematical symbols now. So what they were saying, what they noticed is that when these measurements were made, they had when these measurements were made, they had something that they called background noise. And they noticed that every gene had a different background value. So they wanted to correct for this. So in this model, I have what I want to estimate in beta, and then the background in alpha. So you observe Y, you want to observe beta, but you have this alpha that's annoying and you want to get rid of it because it's just background. So what they did to fix that is they added another measurement that was supposed to only measure alpha. So then you subtract and you're done. That was the idea. Problem was that it wasn't quite right. We ran an experiment where we had just, with a negative control experiment where there's no beta, so it should all be alpha. And when you plot Y1 versus Y2, you didn't see, they weren't on a straight line. They were correlated, but not on a straight line, which actually has a consequence. So a better model would be to say that these two things are correlated as opposed to being the same. And once you write that down, then you realize, you can do some math, to realize that what they were looking at, which is equivalent to looking at the log of this corrected thing, you could show mathematically that the variance of that thing would be inversely proportional to the signal squared, which is what we saw here. You can almost see the 1 over beta squared in that plot. The variance is growing in that way. So you can do, now you can, knowing this, you can find alternative ways to estimate what you want to estimate without introducing this variance. And when we did that, we turned this plot into this plot just by changing the way that you analyze the data. And now you can see that you would be able to distinguish the orange from the black. And going back to our original question, once you rerun the algorithm through the new approach, you turn this plot into this plot, and now we see what we're supposed to see, which are the 5 clusters. So now that's statistics at work, applied statistics at work. Now that algorithm, once we figured out that we could do this, we wrote software so others could use it. And that was one of the first 14 packages in the bioconductor project was an algorithm that did that. And now the bioconductor project has many other pieces of software that do things like that. They do the statistics right. So biologists want to use it and other analysts want to use it. And it's a big project where people can contribute their packages that do things like that. And it's now quite popular. It has more than 1,000 packages that have been contributed, and they get downloaded hundreds, thousands of times a year. All right, so my final example relates to estimating mortality rates. How much time do I have?
You got 20 minutes.
Okay. Okay, so this is where I was born. It's a little island off the coast. No, it's a little island in the middle of the Caribbean. And this is a picture, a satellite picture of Puerto Rico on September 20th, 2017. It's a very big hurricane. Here's some pictures of what the island looked like after the hurricane. This is where I studied math, here, this building. It's gone now. And that was, it was a big storm. We were hearing reports from people living there that things were pretty bad. But this whole story starts in a day that the President of the United States visited Puerto Rico and was congratulating the governor, because you can read it there. He says, "What's your death count?" he asked, and he turned to Puerto Rico's governor, Rosello, and he said 17, and Rosello said, no, 16. So these are 16 people that had died as a direct consequence of the hurricane. The tree fell on them, or the river took them, that kind of death. But what a lot of people were hearing was that number was definitely wrong, and it wasn't because people had seen the river taking people or whatever. It's because they were seeing people dying in the hospitals or dying in the homes because they couldn't get to the hospitals. So that was very concerning. And what a lot of people wanted to do when they heard this, because this sounds like, oh, everything's fine, we don't have to worry, was actually measure death rates. So why do we measure and estimate disease or death rates? There's a long history of this in epidemiology, which uses statistics as their main tool. And I'll give you one example that's quite famous of how important it is to do things like this. This is a paper. You might not recognize what it is from the title immediately. I'll read you some quotes. This is one of the first papers that came out when they started seeing that when AIDS started killing people in the United States. So one of the things that they say are things like this unusual, and I highlight that word, occurrence of Kaposi's sarcoma in the population, multiple sexually transmissible disease, suggests that such exposure may play a role in its pathogenesis. So that's a key word I'm going to come back to. And here's another one where they give you a range of what's normal in a population, and they're seeing things that are way outside of that range. Here's another quote from the CDC in June 5th, 1981. And there's another one. So they're all talking about what's usual, and then they're seeing something unusual. So they're measuring death rates and comparing it to these death rates that are done that are done just by the CDC just to keep track, and they're noticing something different. This is how this was discovered to be originally an epidemic, and eventually, and then that led to investing and trying to find what it was, and that's how they discovered it was HIV, etc. But it all came from monitoring death rates at a certain level. And here's a plot of the death rates of AIDS now that we know it is AIDS. And you can see that while doing this, you can see there was a problem. Now, eventually they found a way to manage it, and now the deaths are much, much less than they used to be. But this requires somebody to measure death rates and monitor them to see if something unusual is happening. Okay, so in Puerto Rico, when that number was being shared by the government, many people were convinced that couldn't be right, and they wanted to hear what's the death rate. Tell us what the death rate is, and they weren't telling us. So let's talk a little bit about why that is and how we can and how it applies here in this case, because it's a little bit complicated. So I'll just start with an example. In 2012, 2,451 people died in Puerto Rico. So is this unusual? What should we expect? So this is 87 more people than the previous year in September 2011. Okay, so is this unusual? Should we worry? All right, that's what we have to figure out. So here's what usual looks like. So it's not one number. This is now the death rates. This is a histogram, basically, of death for the month of September, when the hurricane hit, and across several years. So we go back and we compute this by looking at years' historical data. So that's what usual is. So nothing unusual happened these years. Maybe there was something like some virus or some heat wave or something, but then you have higher numbers. But most years we consider this to be usual. So what we're concerned about is that what we wanted to see was show us the death rates for September so we can compare it to this. That was not something they were showing. Okay, so that's what I just showed you, and what we can figure out from this is that this is just using data from 2010 to 2016. The average number of deaths for September was 2,400, and the standard deviation was 100. And from there, using statistics, we can figure out that 99% of the usual years, the deaths will be between those two numbers. That's one way we can do it. 99%. We can do 95, 99.9, whatever you want, but that's 99. All right, now how about other months? So here's January. More people die in January than in September, at least in the northern hemisphere, and it's because of viruses. But it's different. So that we're gonna see this. But before I continue, I want to point out something every statistician and epidemiologist know, but we really shouldn't be looking at totals. And I'll show you why it's particularly important in Puerto Rico. Demography is changing. So there's 29,900 people died in Puerto Rico in 2011. 29,340 died in 2016. So are things getting better? 560 less. But here's why that's not really the way to look at it. that was the rate in 2011. In 2016, 200,000, more than 200,000 people had left. That's another thing that's happening in Puerto Rico. People are leaving. So the death rate is actually higher. We shouldn't be looking at totals. We should be looking at rates. And what makes it even more complicated, so what explains this is not typical. The death rates usually go down in time, if anything. So why is it going up? This has nothing to do with the hurricane. It's before the hurricane. The reason is because the demography is changing. So these are histograms of age groups, and then comparing Puerto Rico to the United States. Back in the 80s, there was a lot of young people, not that many old people, and that's changing dramatically. Young people are leaving to get jobs in the US. Now we have older population, so the death rate is expected to be higher. There's more old people. You can correct for that. Epidemiologists have ways of correcting for that. When they give death rates, they usually correct for demography. Okay, so now back to October 2017 or September 2017. So should we be worried? Are there unusual number of deaths? Is there a public health crisis in Puerto Rico? So how would we do this if we were able to get the data? It wouldn't be that complicated. We can compute the current death rate, and subtract it from the expected death rate and see if it's outside the usual range. So when should we worry? Well, when it's outside that range. 16 is certainly not outside the normal range for September, but do we believe that number? All right, so we made several attempts. Now when I say we, I mean a group at Harvard, to try to get that data. Other people were trying to get it too. And when we gave up on trying to get it, we decided to run a survey. So what's the idea here is that instead of getting the government to give you the death registry data, you go and ask people, has anybody died in your family? So we organized a team of people in Puerto Rico. They went up everywhere in the mountains. We designed it so they would go to certain places that were representative of the island in different ways. And out they went with iPads to ask people. They would knock on doors and ask how many people live here, how many people died in the last year, when did they die? That was the idea. Now, here, there's going to be a big source of variability introduced by the sampling. We went to 3,000 households, got data for 10,000 people, which isn't that big when you're trying to estimate death rates. But that's what all we could do in the time frame we had. Okay, now in the meantime, others were able to get the data. I don't know how. And they found immediately that there was a big increase. And they estimated 518 for September and 467 that's in October, much more than 16. Here, so then when this paper comes out, we requested the data. They didn't give it to us either, but they had a table in the paper which we could download the table and extract it, and you can make a plot of that. So you can see now the data for the first time we're seeing data for 2016, and you can see that this is the average, a historical average, and here's 2016, and you can see that that's clearly outside the normal range, which is depicted here with the gray area. The New York Times also got their hands on the data, and they had a similar number. This is in October, and I actually called Frances, and she told me it took them 100 phone calls to get that data, and they shared it with us as well. I'll show you that later. Okay, so now, well, this was already published. This is the health minister in Puerto Rico says this. It should be noted that similar numbers are seen in December and January of previous years when no atmospheric phenomenon took place. So he's comparing September to December or January, which we know from historical data that's not what you're gonna do. That's a very incorrect thing to be doing for the Minister of Health. So they were still standing by the 16 number, even after those reports come out. So here's what it looks like, just to show you how ridiculous that statement is. That was a number for September. There's the usual numbers. So now he was comparing it to January or December. There's a number for January. We later got that one too. So even that one was higher than what was expected, which is somewhere in here. All right, so at the same time, so when our survey was going already, so we decided to continue doing it, given that the government was ignoring these findings from others. And there what we do is we estimate the death rate from the survey and then multiply that by the estimate of the population and try to give an estimate of how many people die. So we got that paper published in May, right before hurricane season, and it went a little viral, that story. So even though the other reports had kind of been ignored, this one wasn't. So there's the NPR headline. There was many others, and here's what our data looked like. It's not as strong as the others because it's based on a survey, but I think the fact that it went on for the summer and it was a completely independent measurement from the government's data. It made it so that the media was interested in it. So this is what the data looked like for our survey. You can see there's not that many deaths in a group of 10,000 people. This is the month for 2017, the age of the person, and this is each point is one of the people who died, and you can see that after the hurricane, there's a very different looking set of data points, especially more younger people than 80-year-olds dying. So when this paper comes out, it got to the news. They were reporting the point estimate, which was unfortunate because it was a very wide confidence interval. But it did have the effect of putting pressure on the government. And this is, if you want to see this, is still on YouTube. Is Anderson Cooper interviewing the governor of Puerto Rico, and he really is drilling him not on the numbers, but because when they interviewed us and asked, why are you doing a survey? This is not what you do when you have you have registry data. And we told him because the government didn't give it to us. That's what he was interviewing him about. Why is the data not public? And he was saying that it was public. I have an email, so I know I can show that email to anybody that wants to see it. And he says that it's public, and if it's not, there's going to be hell to pay if it's not public. So then I emailed again, and then they sent me everything. There's a headline. It wasn't just me. They made it public. And I mean, they gave us everything. So here's now that I have all the data, I can show you what it looks like. We even have the causes of death for every person. So originally they sent us a PDF, but more recently they have been sending us Excel files. So. But yeah, I have a blog post about the first data set we got, and you can see that there's like this much wrangling and then this much analysis. So here's the data for 2015. You can see what usual is. And then I put a little lowest line going through it. So this is now daily data. And here's 2000 and there's 2016. It looks very similar. And again, and let me just point out again that December and January, more deaths than in the summer. This is overall. It's one of the interesting things we've seen now is that if you look, this is true for older people. Younger people, the summer is worse because they're out of school probably, right, and doing stupid things. So that looks normal. And then if you look at 2017, this is the year of the hurricane. It looks the same, pretty much, up until September. And this is data that they had all along. That's what it looks like after. That is just, you don't really need to be an expert in statistics to know that there's a problem going on. So now that we have all the data, we can do much more. Now we have more sophisticated statistical models to account for all kinds of things. And we can estimate that increases in death rates That's what it looks like for 2016. You can see the big jump. There's a big increase in death rate. And we started comparing it to other hurricanes in other US cities. And there's nothing like Hurricane Maria, as far as we can tell, with one exception, which is Katrina in New Orleans. That's the pink data. There's a point missing because the point is like way, way out there. The day after the levees break, there was like a 800% increase in death rate. But then after that, it leveled off. But you can see that other places don't have this big effect, and it's not the day of. It's what happens afterwards. So this is a long, lingering effect because the infrastructure is all messed up, because people aren't getting the insulin they need. They're having heart attacks because they don't get to the, all kinds of different reasons. And the other thing we found is that now that we have all the data from Puerto Rico, we actually saw that in another one we had in 1998, there was also a big effect. Nobody talked about that one, but it's probably similar because the infrastructure is so bad that hurricane comes and all of a sudden you have a lot of older people that die that they would have probably lived a few more years if not for the lack of electricity or access to hospitals. So here's an estimate of the excess deaths, and we can see that Georgia's, that one that nobody talked about, is actually comparable to Katrina. In Katrina, you see the big jump. This is cumulative deaths. See the big jump on the day the levees broke, 800 people died. And then it was pretty bad afterward, but nothing like Maria. Okay, and that's the end.
Thank you, Rafa. That was absolutely amazing and very engaging. Does anyone have any questions?